Hi everyone, this is Tutor Marife MCP. I create math tutorial videos that could serve as your supplemental learning resources. In this video, you will learn how to graph this given system of linear inequalities in two variables and how to identify points that belong to the solution set of the system. By graphical method, the solution set of a system of linear inequalities is the intersection region that contains all the points that satisfy not just one of the inequalities, but both the inequalities in the system. Since the graph of each inequality is a shaded half plane bounded by either a dashed line or a solid line, the intersection region is where the shaded half planes overlap. When graphing linear inequalities, determine first whether you are going to use a solid boundary line or a dashed boundary line. We use a solid boundary line when the given inequality symbol is greater than or equal to or less than or equal to. In other words, if there is an equal component to the symbol, we use a solid boundary line. A solid boundary line indicates that the points on the boundary line are included in the solution set of the inequality. For the first inequality, the symbol used is greater than or equal to, therefore, we are going to use a solid boundary line. We use a dashed boundary line when the given inequality symbol is greater than or less than. In other words, there is no equal component to the symbol. A dashed boundary line indicates that the points on the boundary line are not included in the solution set of the inequality. For the second inequality, the given inequality symbol is less than, therefore we are going to use a dashed boundary line. Let's focus on the first inequality. We have y greater than or equal to 2x plus 1. Obtain the equation of the solid boundary line by replacing the inequality symbol with an equal symbol. We now have y equals 2x plus 1 as the equation of our solid boundary line. We have two main goals. First, we should be able to sketch the solid boundary line that divides the xy plane into two half planes. Second, we should be able to shade the correct half plane that represents the solution set of the first inequality. The equation of the solid boundary line is written in y equals mx plus b form, or the slope-intercept form. The value of m is the numerical coefficient of x. M is equal to 2. In fraction form, 2 is equal to 2 divided by 1 or 2 over 1. 2 is rise, 1 is run. M represents the slope of the solid boundary line. B is the constant term of the slope-intercept equation. It's equal to positive 1. This is where the solid boundary line crosses the y-axis. Let's use this information to graph the solid boundary line of the first inequality. Start with plotting the y-intercept. The y-intercept is at 0, 1. X-coordinate is 0, y-coordinate is 1. This is the first point of the boundary line. To locate the second point of the boundary line, use the slope of the line. M is equal to 2 over 1. In every 2 rises, we have 1 run. Remember that when the slope is positive, we have a rising boundary line. That means the line should slant up when viewed from left to right. So from the y-intercept 1, we move vertically 2 units up, then move horizontally 1 unit to the right. 2 rises, 1 run. This is our second point. The coordinates of the second point are x equals 1, y equals 3. Then draw a line passing through the 2 points. This is our solid boundary line. The next goal is to decide which of the 2 half planes represent the solution set of the first inequality. We are going to use the origin as our test point to decide on which half plane to shade. If the coordinates of the origin, x equals 0 and y equals 0, satisfy the first inequality, we shade the half plane that contains the origin. If the coordinates of the origin do not satisfy the first inequality, we shade the half plane that does not contain the origin. Okay, so let's test the origin. Y greater than or equal to 2x plus 1. The coordinates of the origin are 0 and 0. Plug 0 into x, plug 0 into y. 0 is greater than or equal to 2 times 0 plus 1. Any number multiplied by 0 is always equal to 0. 0 is greater than or equal to 0 plus 1 is equal to 1. We end up with 0 greater than or equal to 1. If you're still confused with which inequality sign means greater than and less than, it is useful to remember that the open side of the inequality symbol always faces the larger number. 1 is larger than 0, but the inequality sign faces 0. Therefore, this is a false statement. If this is a false statement, it means that we are going to shade the half plane that does not contain the origin. This is the half plane that does not contain the origin. This shaded half plane, including the points on the solid boundary line, represent the solution set of the first inequality. Let's now focus on the second inequality in the system. We have y less than negative x plus 1. Replace the inequality sign with an equal sign. Y equals negative x plus 1 is the equation of our dashed boundary line. The equation of the dashed boundary line is also written in y equals mx plus b form or the slope-intercept form. The value of m, which is the numerical coefficient of x, is equal to negative 1. In fraction form, negative 1 is equal to negative 1 over 1. The negative sign in the slope means that we have a falling boundary line. The line slants down as we view it from left to right. B, which is the constant term of the slope-intercept equation, is equal to 1. This is the y-intercept of the boundary line. Okay, so let's use this information to sketch the dashed boundary line of the second inequality. Start with plotting the y-intercept. Our y-intercept is at 1. So it's the same as the y-intercept of the first boundary line. To locate the second point, we will use the value of the slope. We have a negative sign, so 1 fall, 1 run. Move vertically 1 unit downward, move horizontally 1 unit to the right. So from this point, we move vertically 1 unit downward and move horizontally 1 unit to the right. This is the second point of our dashed boundary line. Its coordinates are 1, 0. Draw a line passing through the 2 points. This is now our dashed boundary line. After sketching the dashed boundary line for the second inequality in the system, decide on which of the two half planes represents the solution set of the second inequality. To decide on that, let's use the origin as a test point. The coordinates of the origin are both 0. Plug 0 into x, plug 0 into y. If we end up with a true inequality statement, then we are going to shade the half plane that contains the origin. If we end up with a false inequality statement, we shade the half plane that does not contain the origin. Okay, so replace x with 0, replace y with 0. Y less than negative x plus 1 becomes 0 less than negative 0 plus 1. Simplifying right side of the inequality, 1. We end up with 0 less than 1. 1 is larger than 0. The open side of the inequality sign faces the larger number. Therefore, this is a true statement. If this is a true statement, then the origin is a solution to the second inequality. We shade the half plane containing the origin. This is the origin. This is the half plane containing the origin. So we shade this half plane. This shaded half plane represents the solution set of the second inequality. After graphing each of the inequalities in the system, we are now ready to identify the solution set of the given system of inequalities. Remember that the solution set of a system of linear inequalities is the intersection region of the shaded half planes. Okay, so based on the graphs, the intersection region is where the red and green colors overlap. This is the intersection region of the given system of linear inequalities. Okay, this intersection region contains all the points that satisfy both the inequalities in the system. Aside from graphing the solution set of the given system of inequalities, we are also required to identify at least 3 points that belong to the solution set of the inequalities. Points that belong to the solution set of the inequalities are points located inside the intersection region. This is the intersection region. I have redrawn the solution set of the given system showing the intersection region only. This intersection region represents the solution set of the given system. So our goal is to pick at least 3 points within the intersection region. For the first point, we can pick -1, +1. For the second point, we can also pick -2, -1. And for our third point, we can pick -3, +2. Let's verify these points if they really belong to the solution set of the given system by substituting the x and y coordinates into both the inequalities and find out if we end up with true statements. Okay, so let's test the first point. Its x coordinate is -1, y coordinate is +1. Plug -1 into x, plug y into 1. Y greater than or equal to 2 times -1 plus 1. 1 greater than or equal to -2 plus 1. 1 greater than or equal to -1. The open side of the inequality sign faces the larger number. This is a true statement. So this point satisfies the first inequality in the system. Let's find out if this point also satisfies the second inequality in the system. Okay, so again, plug -1 into x, plug 1 into y. 1 less than negative 1 plus 1. 1 less than 1 plus 1. 1 less than 2. The open side of the inequality sign faces the larger number. So this is a true statement. Since we both have true statements, this point really belongs to the solution set of the system. Let's test the second point. We have negative 2, negative 1. Our first inequality is y greater than or equal to 2x plus 1. Plug negative 2 into x, plug negative 1 into y. Negative 1 greater than or equal to 2 times negative 2 plus 1. Negative 1 greater than or equal to negative 4 plus 1. Negative 1 greater than or equal to negative 3. Negative 1 is larger than negative 3. The open side of the inequality sign faces the larger number. This is a true statement. Let's try the second inequality. Y less than negative x plus 1. Plug negative 2 into x, plug negative 1 into y. Negative 1 less than negative 2 plus 1. Negative 1 less than 2 plus 1. Negative 1 less than 3. 3 is larger than negative 1. The open side of the inequality sign faces the larger number. This is a true statement. We both have true statements, therefore, this point really belongs to the solution set of the given system. So for the last point, we have x equals negative 3 and y equals 2. The first inequality is y greater than or equal to 2x plus 1. Plug negative 3 into x, plug 2 into y. 2 greater than or equal to 2 times negative 3 plus 1. 2 greater than or equal to negative 6 plus 1. 2 greater than or equal to negative 5. 2 is larger. The open side of the inequality sign faces the larger number. Therefore, this is a true statement. Let's test the second inequality. Y less than negative x plus 1. Plug negative 3 into x, plug 2 into y. 2 less than negative 3 plus 1. 2 less than 3 plus 1. 2 less than 4. 4 is larger than 2. The open side of the inequality sign faces the larger number. Therefore, this is a true statement. Again, we both have true statements. Therefore, the third point really belongs to the solution set of the given system. Okay? That's it. I hope this video is helpful to you. If you have any questions, you want further clarification, or you want to give feedback on this video, please feel free to post your comments. Again, this is Tutor Marife MCP. I thank you for taking the time to watch my video.